All right. So remember, we are still in chapter 9, okay? And let's see, here it comes. 1 second. At least I think it is. Here it comes. Okay, so we're still in chapter 9, okay? And again, we're looking at probability, and we're still considering, counting the sample space and all that, and finding probability. And remember, as I said last time, you're not going to be able to, you're not always going to be able to list every outcome in the sample space. Or if you have to, you really need some efficient way to list the elements in a sample space. You're not going to have something simple like tossing a coin once or even twice. You could have sample spaces that have, 50 or more items in there. I mean, 50 is not terrible, I guess, but what if you had hundreds or something, I mean, you're going to want an efficient way to list all the elements in a sample space. So what I did, so one way to pull that off is to use what's called a tree. And if you remember the example we did last time, well, I don't think we finished it, but we started it. We were at a restaurant, and we can order an appetizer and a meal. And for the appetizer, we have 3 choices, and we have 5 choices as well for the meal. Okay, for the appetizer, remember, we have soup, salad, or breadsticks we can order. And for the meal, we have 5 choices. We can get a hamburger, a sandwich, quiche, fajita, or pizza. We can get those. And of course, we're assuming also, just to make it simpler, you can only get 1 item from each category. There we go. You can only get 1 item from each category. So we want to know how many different options could you have, though? Well, we can determine how many there are without listing them. Being able to list them is useful. One way to do that efficiently is to use what's called a tree. Excuse me. With a tree, the idea is this. You have a point on top where the branches come from. So I guess in a sense, it's kind of like an upside down tree. And from that point, you have branches coming out to each item in a category. So in this case, the first category we're going to consider is the meal. I know the appetizer usually comes before the meal, but for the purposes of listing elements in a sample space, it really doesn't matter that much. At least for now, it doesn't. So again, you can make a branch from the starting point, so to say. I think they call this a root, but I don't know that for sure. But you have a branch for each item in the meal category. There are 5 choices, as you can see. But that's not all, though, because from each meal, you can get an appetizer, and you have 3 choices for each. So you can have from hamburger, you would have a branch for each appetizer, the element from the other category. Right? So you have bread for breadsticks. I ran out of room, so that's why I wrote bread, soup, and salad. Same thing with the other meal options. You have sandwich, you have bread, soup, and salad. Fajita, you have bread, soup, and salad as well. You do this for each of them. And not only can you actually list all the outcomes efficiently, right? You basically to get each outcome, you start from the top, go down a branch, all the way to the very bottom. The way you get to the very bottom, the path you take, you get an outcome. So you can have a hamburger, then breadsticks. You can have a hamburger, then soup, or a hamburger, then salad. Or you could go down another path, sandwich down to breadsticks, sandwich down to soup, and so on and so forth. You keep on doing this. And each way you get down, each path you take, you get an outcome, as I have written here. You also can get the number of outcomes easily. You just count how many branches there are at the bottom, essentially, right? So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and you keep on going. In this case, you'll get to 15. So that's how you actually can get not only the outcomes listed efficiently, but the number of them. I think what you can also do is you can use a table to list the outcomes. I think the book does that. I'm skipping over that though. So that's the idea with the tree. Okay. But sometimes you don't have to list all the outcomes. You might just need the number of outcomes. That's where the counting principle, as they call it, comes into play. It's also called the multiplication rule for probabilities. Basically here, if you have, let's say, you have to choose an item from 2 separate categories, right? For instance, in this example, if we had to choose an item from the meal category and an item from the appetizer category, so we're choosing something from 2 separate categories. And if there are m items in the first category and n items in the second category, so in this case we had 5 items in the first category, the meal, 3 items in the second, the total number of available choices is m times n, or the total number of possible outcomes then, the total number of items that is m times n. That's what we get here actually. We actually get 15, which is 5 times 3. 5 items in one category, 3 in the other. So you just multiplies what this is saying. Hence the name multiplication rule. And I don't think this is a proof, but the way you could see why this is true is essentially you would draw a tree, or at least imagine drawing one. You know, you do what we did. You would start from a point called, I think it's called the root. Well, we're calling it a point here. You basically would end up drawing a branch for each item in the first category, so there'd be m branches. And then from each item in the first category, just like over here with the meal, we have a branch for each meal, each item in that category. And then from each of those categories, you would draw branches for each item in the second category. So from each of the m items, you would draw n branches. And thus, you would end up with m times n. You know, it's kind of like what we did with the tree. And you could actually generalize this to more than 2 categories, way more than 2. If you had a third category to pick from as well, and if there are w items there, then the total number of choices would be m times n times w. I mean, you would actually have to draw w choices for each branch, w branches, excuse me, for each item in the second category. So for instance, maybe we can consider getting dessert, right? And if there are 4 choices for dessert, then from each of these categories here, you would draw 4 branches, let's say. And then you would have 5 times 3 times 4, or in the more general case, m times n times w. You basically would just multiply is what we're saying. That's how you get the total number of possibilities. So in this restaurant example, as I just said, you have 5 choices for the meal, which is our first category, 3 choices for the appetizer, which is our second category. Not ow, it should be hour. Let me fix that. But I'm sure you can understand what I mean. We have 3 times 5, which is 15 choices. Basically, it's how many branches there are at the bottom. That's pretty much what you end up doing. Or for rolling 2 standard 6-sided die, right? Well, I guess if you want, you're rolling 1 die twice, and you're recording each pair of numbers you roll. Well, how many outcomes are there? Well, from each roll, you get 6 possible choices, right? You know, 6 numbers, 1 through 6. So from each category would be a roll One category would be the first roll, or the first die. The other category would be the second die, or the second roll, I guess. So by the counting principle, there would be 6 times 6, which is 36 possible outcomes, if you're rolling 2 standard 6-sided die. And you could draw the tree, actually. This is what I did here. Well, part of it, at least. Right? For the first roll, you have 1, 2, and then you keep on going till you get the 6. And then from the second die, or the second roll, that is, you have another 6 choices. And altogether, then, you would have 6 times 6, which is 36 choices. Moreover, you could take it a step further. What if we decide to roll a die a third time, or if we rolled 3 die instead of 2? Well, then you're going to have a third category, namely the numbers from the third die, and then you would have, from each roll, from each number, each outcome in the second die, you would have 6 choices, as you can see. And this would keep on going. And for 3 die, you would get 6 times 6 times 6, which is 6 cubed, which is 216 possibilities. Okay. Are there any questions on this?